as security research things he does. He has a good talk on machine learning, and he's spent over a decade doing security research.
Yeah.
So without further ado, Caleb Fenton.
Thank you. Good. Yeah, so I'm Caleb. I recognize some of you, so hopefully I haven't said it. I won't say a bunch of things that you've heard already. But this is sort of the obligatory who I am slide. You can't really read any of the links, but I can send you the slides later. So that's my, it's my Twitter, my blog, my GitHub, it's my squad, Red Naga, that's like my group of friends that I hack around with. You can join our Slack channel if you ever have any questions about Android or reverse engineering or security in general. We have people there who are super senior and people there who are super new, and everyone's super friendly. So if you ever want to stop by. My official title is Head of Innovation at SentinelOne. SentinelOne is a SaaS EPP company, which just means we're an antivirus for people with a lot of money. And what my team does is we build new features and new products that maybe aren't possible or maybe no one else can figure out how to build. Sometimes we succeed, sometimes we fail. If it were easy, it wouldn't be innovation. And if we knew what we were doing, it wouldn't be research. So I have a lot of interests. If you want to talk to me about any of these things, there's not really a relationship to security, but like Bitcoin, I could talk for about 10 hours. I wouldn't just be talking, I'd be listening too, but it's a very interesting topic to me. And I heard if you put a picture of yourself with a dog, people trust you more. So it's me and my dog. Okay, so I want to start with the sort of cool stuff I hope you'll learn from this talk. What I hope that you will sort of ingest from listening to this is why machine learning is exciting, like why it's interesting, why you might want to get started in it, why you should care. It's actually much more approachable than you might think. It might sound overwhelming, but it's not. So I want to teach you a little bit how it works. So instead of, this is just a talk and it's really just 30, 45 minutes. I'm not going to be able to go into extreme detail and like debug code with you, but I can at least give you lots of terms and vocabulary and concepts so you know. It's basically everything I wish someone told me when I first started. It would have saved me a ton of time. I had to learn this stuff really the hard way. And then I'll go through an example of how you might do machine learning to detect Android malware. It's easier than you'd think. And then there's a ton of resources in the slide deck for experimentation. So that's data sets, videos, sites with like coding challenges and stuff. So I'll go through that at the end. So first, why is it exciting? It's being used for all sorts of cool stuff, way outside of just security and detecting malware. So there's simulating physics or learning physics. So let's say, I'm going to make a lot of game analogies because I'm talking to college kids, right? So if you're making a game and you want to have physics in your game, you can either hire 40 people and spend 6 months building a really good physics engine, or you hire like 2 data science people and you spend a couple weeks processing some numbers and it will learn the physics for you. So you save a lot of time, you save a lot of money, and it might even be more realistic physics. There's generative networks. These are usually neural networks that are generating something. So they're generating an image, generating textures, generating video. This is deep fakes. So putting your face on, or maybe like animating Barack Obama's face with whatever you're saying. Like that, you might have seen something like that. And then there's the classification problem, which is what you'd be using for malware to classify something as either good or bad. And that's really what I'll be talking about mostly here, but I'm going to show you some animations of the other things. So the physics simulations, this is an experiment done with cloth simulation. So they used machine learning to figure out how to simulate the physics of this cloth. So they didn't have programmers decide how physics and air friction should work. They learned all of these things. So a small team of people is able to create or generate these types of physics. This is pretty cool. This is actually, you can do this on your phone. This is a website. You can go in and you can say, I have this picture. I want to add sky. I want to delete grass. And I want to make some domes here. You can add doors to the picture. And this is a generative neural network. So you can, I would say this is probably how photo editing is going to work in maybe a couple of years, where, oh, I really don't like that person in my picture, and they're just gone, and it looks like they were never there, and you don't have to pay $300 for a Photoshop expert. The machine learning knows how to do it for you. This is cool. This is AlphaStar, which is from Google. just destroying some of the best StarCraft 2 players in the world, crushing them, using strategies that these players had never seen before. And it was limited to the same sort of actions per minute that a human user would have. So given the same constraints as a person, this AI was able to play against itself and play against players and get better and get stronger to the point where it was doing things with the game that people had never thought of doing. It was strategies that they didn't even think should work. And you can see, there's a really good video, you can see the link on YouTube that explains like, what all these cool human features are. It's pretty advanced, but it's also, the concept is pretty simple. You can probably build something yourself with Mario in 3 to 6 months. And this is classification. I know this looks a little dumpy compared to everything else. It doesn't look quite as cool, but this is what machine learning is doing. You have 2 classifications. You have the purple dots and the yellow dots. And if you are a machine, maybe you don't know, just starting at the beginning, which is, we're near the end here, but now you're at the beginning. You can't really tell, except they're colored, which one's which. And what machine learning is going to do is going to sort of skew and move around the feature space and try to draw this decision boundary. So in this case, you have 2 features, the x-axis and the y-axis, and every dot is a sample that's plotted with its feature value. And the way the math works out behind the scenes is it's squishing the feature space up and then trying to draw that line between the 2 classes. So there's tons of other uses for machine learning. There's voice text synthesis that has some security implications. What's going to happen when I can have a perfect or near perfect replica of your face and your voice calling your boss, asking to send you your password or something? What are we going to do then? There's also voice and text translation, object recognition. That stuff's really already taking off. Autonomous vehicles, also known as the other AV. I work in antivirus, they're the other AV. And then sort of Skynet, general AI, Terminator, end of the world type stuff. So with classification, the type of classification you're usually using is binary. So it's either good or bad. So binary classification is just a fancy phrase, good for you to learn. It's not normally this slow, it's because I converted it to PowerPoint. The way you would do this, you'd start off by getting a good data set. So you collect many different malicious and many different benign samples. So these are Notepad and Calculator and the video games you play and any other benign applications you would have. You would give a giant pile of those, you have a giant pile of malware, and that's your data set. And that's what you would start with. You would take that data and you would use a machine learning algorithm to train a model to learn the difference between good and bad. Essentially, this is what you would do if you were an analyst and you're trying to learn how malware worked. In a very real sense, you're training a program to do one very specific thing. And it might be something that you do right now, but it's learning how to do it for you. And then on the endpoint, you'd have your model that has learned to tell the difference between good and bad. You'd monitor for new files, scan it with the model, and delete it if it's bad. And help, I've automated myself out of a job. When it comes to automation, there are people who have 45 minutes of videos on YouTube about automation and AI and how scary that is. Essentially, so far, what it means is you get to work on more complicated, more creative, more interesting problems, while the machines do more and more of the boring, repetitive stuff. At least for the next 5-10 years, that seems to be the case. So a quick overview of how this stuff works. A picture's worth 1,000 words. Big pile of malicious files, benign files. You extract features. How random does the file look? Or what we do with computer science call entropy. It's a measure of randomness. What's the entropy of the file? How big is it? What sort of strings are in the file? I'll give some examples of features later. Train the model, and that's surprisingly easy to do. There's libraries and there's code that do a lot of this for you. And then on the endpoints, you extract features from any files you see, you give it to the model gives you some output, usually a number between 0 and 1. And that's how you decide if it's good or bad. So you need to build a classifier. We already talked about collecting training data. We talked about engineering features, so that requires malware knowledge. You need to understand what malware is going to be doing that you might be able to extract from a file. You need to be able to understand the file format really well. So if you're doing Windows malware, you need to know Windows files very well. If you're doing Android very well. But if you're trying to generalize this lesson to any type of classification, you don't have to, if you want to experiment with this, you don't have to start with malware. You could start with something simple like sentences. You could try to find sentences that sound like they're being mean versus sentences that sound like they're being nice. Because you know English, you can think of words. If it has if it has expletives in it, then it's probably being mean. You know what expletives are, so you could have those as features. If this sentence contains the F-bomb, then maybe that's bad. Extract that as features and give it to your learning algorithm. Then after you engineer features, a lot of people don't talk about this. If you watch a lot of machine learning like tutorials or lessons or blogs, they don't tell you how important it is to explore your data. I guarantee you, if you're a human being writing code, you're going to have bugs. You're going to extract features badly. You're not going to do it right. The customers are going to complain. So you need to be able to know how to explore your data and understand features, and I'll explain how to do that. So then the process is you constantly train and tune and test your model, and you go through refining that process over and over again. But if you're doing a production system, if you're just trying to get a PhD, then you don't have to do all that. You just have to worry about doing something novel. So of course, you repeat those steps forever. And most people get the most mileage out of engineering features. This is another thing no one tells you. If you're actually in a real environment where you're trying to do this as a company, you wonder where should we spend all our time? Should we spend our time adjusting the machine learning, or should we spend our time doing better feature extraction? It's engineering features. Feature extraction is by far the most important. You can do lots of tuning with models, but essentially the better your features, the better the information is that's going to be going to your learning algorithm training. Okay, so we've gone through the steps. We talked a little bit about how to collect data, what data are important, and this you can generalize to any sort of machine learning. This isn't just about malware. Customers always ask, use neural networks. We heard those are cool. I tell them to shut that down immediately. So that does not matter. If you want to really kick the tires and really evaluate a machine learning solution, what you should ask is how do we know our data are good? And you can really win some bonus points if you use data as a plural, because it is. So it's like that's our secret sauce: garbage in, garbage out. So what is good? It should represent what's going to be in the wild, wherever you're going to use your model. It shouldn't be some toy data set that you have. It should try to represent the wild. The technical terms there are high variance, so it should be varied, and low bias, meaning it shouldn't be from just a single source. So the way you do this is you collect it from many different sources. So if I'm doing malware, I'm going to try to collect files from every machine in this room. I'm going to want to collect files from your machine. I want to collect files from Ubuntu's source repository. I'm going to want to get files from Softpedia, from download wherever. I want to get all of the different files and all of the different malwares. Crawling sites, customers, and then you're doing constant feature engineering and tweaking. That's another part of your data, is how good your data is, how good your features. If you have really good malware people that really know this stuff, they will come up with some really interesting features that are specific or endemic to either goodware or malicious files. This is a really good way of learning high bias or the bias variance trade-off. So top left is it's good because you're in the dot there, so it's low bias, but they're really tightly centered. So maybe it's malware, but it's all one family of malware. And then bottom left is high bias, low variance is probably the worst. So you've collected a bunch of data that have nothing to do with what's going to be in the real world, and they're all pretty much the same. Then bottom right is you're good, it's varied, it's nice, but it's not really something that you're going to expect to see in the wild. And then top right, it's high variance, low bias, that's ideal. It's going to be centered around stuff you see in the wild, and there's going to be a wide variety there. This is the mental picture you should have in mind when thinking about, do I have enough data? So that's collecting data. Now we're talking about engineering features, sort of breezing through this. So what is a feature? Here's an example of a feature. I hope you haven't seen this before. So this is how you can tell if someone's good or evil, if they have a goatee or not. Very simple feature, works in a lot of comic books.
Look like Simba.
Yeah, you can. I mean, the guy really does look evil. He looks like Satan. But a more realistic example is this. This is a decision tree. This might seem simple. This is like an if true, if false. Believe it or not, our product, which we were selling for millions of dollars, whatever, was using a whole bunch of decision trees. So understanding decision trees and how they work is actually pretty important. It wasn't 3 layers deep, it was maybe 200 layers deep. And the features were very different, but essentially this scales really well. So in this case, this will tell you if something is a dog or a cat. So you follow through, you start at the beginning. Does it love you? False. You go to the right. And then all at the bottom here, you can see all the examples on the loves you. It's probably more likely to be a cat, because cats don't really love anybody. So if it doesn't love you and it has sharp teeth, then it's very likely a cat. So if it does love you and has an excellent sense of smell and it wears a leash, then it's most likely a dog, because cats never wear a leash. So keeping to that analogy, I'm going to test the audience, right? So, you don't have to say this out loud. You don't spoil it for anybody. If you look at this picture, tell me what you think, or just think what you think it is, right? That's a cat, spoiler. And then here, we'll give this a couple of seconds. This is a dog. Good, yes. What about that? It's a little harder. You can still probably guess. What do you think? Yeah, you're right. It's a cat. How do you tell it's a cat? Yeah, really? How do you tell? Tail, yeah.
Doesn't have a leash.
Doesn't have a leash, yeah. So I looked at the paws, but the tail's good too. Yeah. So you looked at it for a second, maybe you looked at its face and were like, oh, that's not good. I need to look at other features, more informative features. So what happened? Your training data probably wasn't good enough, probably didn't include cats with this particular disease where their fur never stops growing. But these cats exist in the wild, so your data was a little bit lacking. What's it called? Hypertrichosis. I wonder what that looks like in humans. So now your internal model has improved. You've trained on that data. Now, literally, your neural network has learned to recognize cats with hypertrichosis. You've learned to zero in on those features that are more indicative of a cat versus dog. So maybe tail in your case, or paws in my case. And machine learning works the very same way. It's like feature extraction is so important. If all of your features were about the face, then maybe your algorithm would fail. So just to talk a little bit about Android, and I can go through this pretty quickly because this is a little, this would be something that you could reference in the slides later if you're interested, but it's a little technical. So Android apps are really just zip files with the APK extension. There's a lot of variety inside of APKs. There's the manifest. The manifest will tell you everything that the app will do, the permissions it uses, if it sends text messages, if it uses accessibility features. It's super useful if you're a reverse engineer because it tells you everything the app's going to do or can do. Then there's the executables inside the zip. There's a signing certificate, so every app has to be signed by a developer. You can extract features from that. And then there's lots of resources, so icons, maps, sounds. We have a whole series on this that we did at DEF CON for how to really tear into these. There's a really good explanation on this here, if Android's interesting to you. So for example features you might extract from the Android app are what permissions does it use? Does it send text messages? That's really important. Does it ask for device administrator? Some legitimate apps use device administrator, but malicious apps use device administrator to keep them from being uninstalled. So maybe device admin isn't enough, but if it's device admin, if it requires device admin and it's a very small application, then it's more likely going to be malware because malware usually doesn't have a lot of code in it. So you be sure to include the file size as a feature, and now all of a sudden that maybe one feature is not enough to tell good and bad, but the collection of features is. Uses accessibility services, so watching what you put on the screen, dynamically loads code if it's debug signed, compiler fingerprinting. This is all sort of covered in the DEF CON link that I had earlier. So these are some feature extraction tools. I said this stuff is pretty approachable. You can download a bunch of these tools and you will have a library that can do the feature extraction for you. This does almost all of the feature extraction you would need, and you're just doing the normal. If you're an actual data scientist, dark secret is you're going to spend half your time massaging data and cleaning data. So this does most of the heavy lifting for you, and you do normal data science stuff with this. So that's how to engineer features. We're getting there. We're number 3 out of 5. So now it's time to explore the data and make sure that you don't have bugs in your features and that your data makes sense. And this is another artifact of translating it from Keynote to PowerPoint. So the first visualization you look at will always reveal a data quality error. And if it doesn't reveal a data quality error, that just means you haven't found one yet. And I found this to be true. Your data are always crap, and you're always fighting against time and against the data to make the data clean and useful. So it's always good to try to look at it a couple of different ways to see how dirty it is. First thing I do is look at the label distribution. You're going to have a bunch of malware and a bunch of benign files. One of the problems we have with Linux executables at my job is we have a teeny tiny number of malwares for Linux, maybe 100, 1,000. And we have 100,000 examples of benign files. So that's kind of bad. You want to evenly distribute those labels so that you can train on both. If you can't, there is something called weighting, where you could tell your learning algorithm, if you miss a malware file, then you should take that very, very seriously and adjust accordingly. So there are ways of dealing with it, but you want to make sure you're balanced if you can. You're also going to want to look at which features don't vary. So if I had a feature extraction algorithm for people, and one of the features was is human, it's always going to be true. If I extracted your features and your features and your features, it would always say is human, 1. And that would be useless because it wouldn't vary. You're going to have features like that eventually. So there are ways of doing that. You look for invariant features. They're probably not very informative. You're going to want to know which features correlate to target, and there's feature scoring methods for this. Those tend to be more informative, and those can also guide your efforts on where you should do more feature engineering. So if you have one feature that's really good, maybe you can break it up into 2 or 3 that are similar that might also be good. Skip that. So this is sort of the distribution of values. So this is the string count divided by the executable size. So you can see that this is a normal distribution. You don't have a ton of strings in a lot of files, and you don't have a tiny amount of strings in files. Most files have sort of an average number of strings. So this sort of bell curve here is called a normal distribution. This is what you'd expect to see. You'd expect to see strings inside of a file to be sort of normally distributed. Think about your source code. When you're writing a program, you're going to have a string, something surrounded by quotes, every now and then. If you had no strings in your code, that's kind of unusual. If you had a ton of strings in your code, that would also be unusual. This is really cool. It does more than just look cool. This is called TSNE visualization. And this is a really nice way of, whenever you do this stuff, you're going to have maybe 30,000 features, 50,000 features. And there's no way to visualize that unless you're an alien or a robot or something. You need to do something to sort of squish that feature space down in a way that's still informative. And TSNE is a good way of doing that. So there's a whole article there for your perusal if you ever want to visualize that data. By the way, this is some of our own data. What I learned from this is that a lot of our malware was cleanly separable. Like you could see that there's a sort of shell of bad stuff on the outside. And so our features were informative enough to cleanly separate between different clusters of good and bad. And there were many different types of bad. So it wasn't just bad all and lumped together. It was many different types of bad that we were seeing. That was interesting. Okay, so we've collected data, we've engineered features, we've explored the data. Now it's time to do the fun stuff, which is training a model and replacing yourself with a robot. These are all the different models you could use. It's good to just learn these as vocabulary so you sound smart when you're talking about this. This is how they learn. So earlier I showed you the purple and yellow, and it's drawing the line between the two. The shaded areas are how the algorithm is sort of look at the feature space, and it's going to try to draw that line. So I mentioned earlier decision tree. You can see it's kind of simple, it's blocky, it doesn't have a lot of nuance or subtlety or robustness. But a random forest, which is just a collection of decision trees, has a lot more subtlety, has shades, it can break things up a lot better. It can sort of carve spaces out. It's hard to see in this projection, but you can see it better in the slides. So it's good to keep an awareness of the different algorithms and how they learn. Then there's overfitting. This is something you're going to need to know about if you're ever actually doing this stuff. You can see this green decision boundary. It is perfect. It cleanly separates all of the red and all of the blue. Everything on this side is blue, everything on that side is red. It goes way out of its way to carve out that one red dot who's hanging out with all the blue dots. You might think that's good because now you have a model that's perfectly accurate. But this is actually very bad. It's not generalizing, it's memorizing. It's like if you memorized all the questions and answers on a test. So you really want to generalize something that is really trying to learn the difference. And yeah, you're going to get some things wrong, but this thing probably isn't learning. It's probably just memorizing. And here's an analogy, and this is actually applicable. This is how the machine learning algorithm is working. You have a math test. You study by memorizing the problems and answers. You test, but the test questions are slightly different. They usually are, unless you're lucky and you have a really easy math teacher. You don't know how to answer if you get to the test and they're slightly different than what you memorized. You screwed yourself. So you should remember that general relativity is better than special relativity. You always want to generalize the pattern. You don't want to learn how to, if you're in calculus, you don't want to learn how to integrate that one problem. You want to learn how integration works. You want to be able to integrate anything. So the way you deal with that is cross-validation. This is another thing I wish someone had told me about when I first started. Very simple concept. Instead of training one time, training the model and then testing, you train it maybe 10 times, and you train with 90% of your data, and you test with 10% of your data. You get that score, you train with a different 90% of your data, and test with a different percent of your data. And you shuffle all that together, and then you average all of the scores up. So a really quick analogy there is you have a physics test. Textbook has 100 questions. Work any problems with Google and check answers. I'm sure you guys have done that before. Or Chegg, or I'm not sure what they use anymore. I have to pay for it. So use the remaining 20 problems as a practice test. And then this is the hard part. You develop really strong amnesia and forget everything you just learned. You repeat that 9 more times, working at different 80 problems with testing yourself on a different 20 problems. And you average all those scores together, and that's how cross-validation works. The reason cross-validation is important is because when you score your model with cross-validation, that's a true representation of how good you're learning this stuff. And tuning hyperparameters. Hyperparameters is what you call parameters in machine learning. So you get to put hyper on it, and it sounds cool. So the models or the learning algorithm, they have different hyperparameters that you can apply to them. So there's loss function, different algorithms use different parameters. You can't know the optimal values in advance. You could be a quadruple PhD and being the head of Google AI research, and you will not know the best way to train on data. It's impossible to know. There's no such thing as a free lunch. You can't know it a priori. You have to try many different combinations. If you're experienced, you can reduce the search space of combinations you need to try. So instead of trying 1,000 things, maybe you just try 20 or 100. But there is something called grid search, which will go through every permutation of parameters possible for a model that you give it, and it will see which one works best. That is really just brute force. So that is the state of the art right now, is you just brute force the parameters until it works best. And that is actually how people do this. There's actually a smarter way than brute forcing. This is something I wish someone had told me also. There's Bayesian optimization, which, again, this gets a little technical, but instead of trying, let's say you have 1,000 different permutations. If you remember from discrete math, permutations are the one there's a lot of. If you have 1,000 different permutations for your parameters, then maybe you just try 10 or 20 spaced out evenly across how they could be permuted, and you see how well they do. You sort of like take some guesses. And then from those guesses, you can use math to tell you which other guesses you should make that are probably closer. So in this, the red points are, the target, which is the actual function, is this blue line. So you want to find the place on the blue line that's highest, but you don't know what that blue line is. So what you could do is you could evaluate that function at every point on the blue line. It'll take forever. It might take years. Or you could just take a couple observations with those red points. And then with those red points, you can make a predicted function, which is that dotted line. So with just a couple of points, you are able to predict what the actual function looks like. And then you could pick that 2 is probably the right value for you, or 2.2 would be the highest value of y of that function. I'm going to skip this. It just looks cool. This is another important thing I wish someone had told me about when you first start. You want to know how good your model is more than a cross-validation score. You want to know how robust it is to false positives. So this is the ROC. This is 3 different models that I'm evaluating. There's one of them that's using, these are different hyperparameters that I'm testing. As the line goes up is how much stuff it's detecting, and as it goes off to the right is how many false positives you're getting. So you want your line to go straight up and to the right. And I don't think I have time, like, I would like to explain this to you more carefully, but I think this is something you can learn on your own if you just read about it. This also means that the area under the curve is a really good proxy for how good the model is. So your cross-validation score and the AUC of your ROC, some terms to learn. There's another curve that took me maybe 2 years to find out about. This will tell you if you need more data. So you want to know, hey, I have 100 million samples. Is that enough? Well, you could test yourself at 10 million, at 50 million, at 90 million, and at 100 million, and you can see what that curve looks like. And if you're getting better with every new sample you add, then you should probably add more samples. But in both of these cases, the curve starts to level off, so maybe you don't need more samples. And finally, there's model stacking and blending. This is a really sort of advanced feature. It's actually probably a little bit harder than everything else I've been talking about. All those different algorithms have strengths and weaknesses, but you can just, again, just brute force stuff. You just train a whole bunch of them and then squish them all together. So instead of saying, hey, model, is this good or bad? You ask an ensemble of models, hey, all you models, is this good or bad? And on top of that, you can have a bunch of models trained, and then you have another model which learns off of those models. So it would be like if I was the CEO, I'm not going to do the nitty-gritty details, but I'll have people report to me and tell me their opinions, and I'll average their opinions, and I'll decide what to do. This actually is how you win a bunch of competitions. This is what wins all the Kagels and all the Netflix competitions. So we've talked about collecting data. You want to have high variance, low bias. You want to test different models and parameters because there's no way to know. Avoid overfitting with cross-validation. Understand performance with receiver operating characteristic. And then there's a learning curve to know if you need more data. Some cats look really weird. And then try it yourself. This is the last part. This is it's good. I'm getting a thumbs up for using XKCD. You got to have one in your presentation. So this is real. This is the reason this is funny is because it's accurate. So this is your machine learning system. Like, yep. You pour the data in this big pile of linear algebra and collect the answers on the other side. What if the answers are wrong? You just stir the pile until they start looking right. And this is sort of like the sort of funny truth to doing machine learning is there's a lot of guesswork and brute forcing that goes on, even in really advanced high-level stuff. So that is a bunch of bullet points with links. That there are whole data sets on malware that you can get. There are classification contests that give you data set that you can get access to. There's that Kaggle blog that talks about all this stuff in detail, really approachable. HackerRank, really cool website if you're not already using it. It's really nice. It's like a gamified learning system where you have challenges and you can gain points and level up, and they have an AI section that I've done it, and it's pretty good. And then there's a video on YouTube. It's called How to Build an Antivirus in 5 Minutes, and it works. Like, it's true. Your main limiting factor there is just getting enough data. But you can, if you had enough data, you can build one in a day. Wouldn't be great. It would only be like 95% accurate. You'd never want to run it on a machine. And then there's also scikit-learn. These are good libraries for you to play with. NumPy, SciPy, Pandas, Matplotlib. All of these make me feel good just to say them, so they're nice. There's a really good YouTube channel called 2 Minute Papers. This guy is super excited about machine learning, and I just like stole a lot of his material for those cool GIFs in the beginning. And every day there's a ton of them. There's lots of free data sets too. And you can't read any of this, but there's lots of malware-specific data sets, and that's it.
Awesome. We're gonna switch to the questions part, and
while you're doing that, would you be available if some of these folks have questions, and let's say, would you be willing to spend some time guide them? Okay, you may want to try this, you may want to try that.
Oh yeah, absolutely. Yeah, I would say either email me or hit me up on Twitter or Slack. And I think this stuff is really cool and interesting. I think the more people in the world that we have working on this stuff, the better the world will be in 10 years.
I'll go first. So our team here, I think, Wendy, you are contributing to secrepo.com, right? So we are working with an open source repository, which is called secrepo.com up here. And so this is a repository of like
Static.
So it's basically a repository of security related data. So if we were to, so this at this point gives a good learning point for people to play with machine learning data.
Yeah.
And what we would like to do as a next step is make it easy for people to learn in this domain. What would you recommend for something like that?
Oh yeah, for this, that's a good point. And I forgot to mention this. For a lot of this, for a lot of security applications, there's anomaly detection. So that's a big part of it, and that's a specialized case of outlier detection. So that's clustering, unsupervised learning. So you take a bunch of data that's not labeled, you don't know if it's good or bad, and you could use different types of clustering, k-means or density-based clustering, and you could see what isn't fitting with the norm. And so you would extract features from these logs, you would extract something that you think you might want to see as an analyst that had like really, really good math skills. What would you want to know? And then you would feed that to a clustering algorithm, and then you I would try to visually represent it in 2 or 3 dimensions or use TSNE and try to visually understand what's going on there, so I know if I'm going in the right direction. But you could probably pull some interesting stuff out of this. If the logs indeed show anomalies, you should be able to cluster it with good features and see that stuff. So I would use clustering there. Yeah.
Awesome. And so as an educational tool, you would recommend that maybe the next step here we do is we kind of run different models on it and do a TSNE visualization for people to start somewhere with that data.
Sure.
And get an idea of whether data is good, like it represents like real world, or it's biased. Right?
Yeah, yeah. And
So,
sklearn's website has like code, like 5-6 lines of code. You could just go and a lot of their clustering algorithms have documentation where you can see exactly what you need to do to make a data set and cluster it.
right. So just for example,
yeah.
like we have a Jupyter notebook for this network data, and what we basically try to do is just kind of give some idea on that data. So you'd think like just a visualization which shows that how good of a data quality it has would be interesting.
You could whenever you want to visualize it, you have to do dimensionality reduction. There's lots of different ways to do that, so you'd experiment with all of them. So do principal component analysis, PCA, do truncated SVD, do feature agglomeration, and all of these sound fancy, but there's like, you just change the API call in Python. Instead of PCA, you just delete it, type truncated SVD, and you run it in a notebook. Notebooks are amazing for data science because you can do experiments and repeat them and very quickly not have to rerun a whole script over and over again. So you would want to reduce the dimensions. You can also use TSNE for that, and that should help you get a good visual of your data.
Awesome. Thank you so much. Sweet. So we are hold on, sorry, my bad. Okay, sweet. So question, I think Alejandro, you had a question?
Yeah,
Is that your question? Have you encountered any attacks which bypass machine learning detection?
Yeah, there's not in the wild. Although advanced attackers might be using this stuff and we're just not detecting it. There are people who have gotten, I would say, some fame and notoriety for getting talks accepted to conferences with coming up with ways around this stuff. So using AI against itself is pretty rare for security, for file-based malware. There are some really neat applications. I blogged about this. You take a picture of a panda, give it to a machine learning algorithm, it says, hey, this is a panda. And then you give it to this other sort of evil script, and it will change pixels that you can't really see. You might have seen this before. And it's like, oh, that's a giraffe. But to the human eye, it looks like a panda. So that's, there are ways of dealing with that, but I think that's one of the ways that's going to need to be dealt with is we're going to need to move away from these dense neural networks to sparse neural networks. There's some theory that needs to evolve there to make these things more robust to these types of attacks. So I think it's partially a solved problem. And then there are other attacks against machine learning solutions. So one of our competitors just got egg on their face because they had a really bad vulnerability in their machine learning detection. But it wasn't necessarily the machine learning that was attacked. They were doing something kind of simple, and attackers found a way to take advantage of that simple heuristic. And then the people writing the blog made it sound like the machine learning got attacked. And so they got a lot of clicks. And unfortunately, the competitor looked bad, but really they just made one dumb mistake, kind of. And it wasn't the machine learning in general that was broken. But yeah, anytime you're really a problem to attackers, they'll find a way to break you. There's money, there's incentive, and there's food there, and they're going to find a way in.
This may not be a technical question, but from the two speakers, we got a very nice introduction bio. I think that you skipped that part. And then now we have heard of all of the impressive things like this. Can you kind of share your personal stories of why you got into this and why you got this exciting technology coming, working in cybersecurity?
Yeah, sure. I partially skipped it because I think one or two of these people might have heard it before, and I've timed this talk. I know how long it takes. Yeah, so I got started I guess I was like 10 years old, and I went around the neighborhood looking for people who can program, knocking on doors. And I found a kid who programmed BASIC. So Brian got started with BASIC, I got started with BASIC. It was a great language, I have a lot of fun there. And then actually there's some patterns I would like to generalize out of your life story, Brian, is that you notice he started fixing people's computers, but then he very quickly went to working in Washington. And like he went through a series of vicissitudes until he was eventually, you didn't mention it, but you're traveling all around the world, like tracking down hackers. It sounded really exciting. And I think that's really applicable here. Like if you get started somewhere, you'll be working, maybe you're fixing computers, maybe it's kind of boring, maybe it's kind of simple. But if you use it as a stepping stone to get to the next level, if you're smart and you work hard, that will always happen. Security is constantly changing, and you'll find a niche and you will move up. I have not seen anybody who was smart and worked hard not do well in this industry, ever. Unless they were really a total jerk to work with. So don't do that either. So for me personally, yeah, I started at a young age, but I don't think that's important at all, because when I moved to California from Texas about 7 years ago, before that I was a network admin and a database administrator going to college for 5 years. And then I moved here and I worked with real engineers. I learned more in a month than I learned in 5 years programming by myself. So having other people do code reviews and having other people who are smart be around and knowledgeable be around you was super important. I would go home at the end of the day and just lay on my face and just listen to sad music, because I was used to being the smartest person in the room. And then I moved here and I was nothing. And there were people way better than me, and they didn't even care about computers. They're just like, I got into computers because I heard you can make money. It's like, bro, I live this. This is my life. How are you smarter than me? Like, I try so hard. And that was really useful to me to really put me in my place and learn my place in this world. But it was also a really good learning opportunity. If you're the smartest person in the room, like, go to a different room. Like you need to be in a room where you're the dumbest person in the room, and hopefully everyone there isn't a jerk to you, and then you can learn stuff.
You have an XKCD by Finn over there.
I don't want to read it. I can't see it though. Yeah, if you haven't heard of XKCD, it's this guy's. He steals my ideas. I'm serious. I think he's got a camera in my house somewhere, because I have come up with the exact same things he has. Oh, this is really good. Yeah, I've started doing this in conversation now. Yeah, it's true. It really does work the same way. And sometimes if you're wondering why something isn't working with your algorithm, if you just keep in mind that it's trying to learn, and you need to be really careful on what information you're giving it to learn, that will help you sort of keep centered and maybe help focus your efforts on what you need to do. I'm sorry, is that enough of a bio? I don't want to talk about myself too much.
Talk more.
We'll take a couple more questions. He's very approachable, and he's been a great supporter of all our students and work. So he's available for students to interact. Cool. More questions? Maybe I have another one. So our students always start with like pandas and Jupyter notebooks, do some kind of analysis or categorization problems, classification problems, and then they kind of get stuck, or they're like, oh, there is so much happening here. I'm like, I can't really do this, or can't do data science, or I can't really do machine learning because I'm just not like up to date with everything happening. So for someone to start after 3 months, like after 3 months of knowing this stuff, how do you kind of keep learning? And like, if you don't have a job which lets you do this every day, how do you find a job, internship, or how do you keep learning so that you don't get disheartened?
Yeah, it's a great question. I had that same sort of weak moment when, since what I do is innovation, that means it's really cool, and then I switch to something else, and I hand off this project that I love and I've cared about intensely to someone else, and then I have to kill that part of me and then do something again, like totally different. So I had that same problem where I did machine learning at work, it was great, and then I stopped doing it at work, and I really wanted to continue to learn more. So I built a bunch of libraries to do feature extraction for Android, and I put them on GitHub. I found other people working on projects on GitHub, and I submitted to them. For me, it's really nice to have that feedback of other people downloading. Like I look, how many people visited my app? How many people started? How many people use it? How many people had complained about it? I like if people raise issues, it means they're using it. Or I go to conferences and I talk about the tools, because you'd think, as an engineer, you solve a problem, you put a piece of code on the internet, you give it to the world, that it's solved, and everybody in the world will rejoice and use it. And that's not exactly at all what happens. No one even knows it exists. So you go to conferences and small meetups that you just apply to go there, and you talk about your tool, and people will learn about it. So you get that feedback of people using the stuff you make. That's great. And then eventually, what happened with me is a group called Polyswarm, which if you just keep knocking on doors, eventually one will open. So I kept doing machine learning. I kept doing sort of like hustling at home and just playing with it and learning with it. And then eventually a group came to me and said, hey, we will give you some grant money if you can build one of these engines. Cha-ching, now all of a sudden I have like a actual like something I could justify to my wife. Like, why am I spending time on this instead of spending time with you? Like, here is an amount, with it. And she's like, oh, okay, that's okay then. And then it's also important to you because you know that someone's valuing what you're working on. So you try to get value from feedback from the community and people using your tool. And then eventually maybe someone will want to buy that from you. There's no reason you can't be an entrepreneur and sell this stuff.
Awesome. Cool. It was good time. We're just at 7:02. Thank you so much, Caleb. Can we do a round of applause? Sweet. I know if you guys have questions, do you guys have time to be around for a little bit? Okay, cool. So if you guys have questions, feel free to just go to the speakers and talk to them for a few minutes. And then next session, we have Mel from Airbnb talking. She's also going to be here in person. If you know any other friends who are interested in cybersecurity and finding internships at Airbnb, then you should encourage them to attend. And the students will also find a lot of value in learning from her because she's comes from a networking background. B, she's a female, and C, she's transitioned from a non-security job into a security job. So all those things would be interesting to learn. Sweet. Yeah, say again.
Yeah, 2 on.